So lastly, a rationale here for melting points and boiling points. In a solid, the molecules are closely packed together, and so each molecule will have interactions with molecules around it. In order to turn into a liquid, where the molecules can freely move around, you have to break those interactions with the neighbors, or at least most of them. So you're going from a structure that's, as a solid, has lots of interactions in a highly defined structure, to a liquid, where there's still many interactions, but the structure is not defined and the molecules are moving around a lot more. And so energy is required to break up those interactions and allow the molecule to move around and flow freely. In that liquid, again, the molecules are closely packed, they're just flowing around freely. But to boil, we need energy to break all of the interactions and put it in the gas phase where essentially it's alone and it has no intermolecular interactions. Okay, the last thing we want to do is a problem. Okay. So copy these molecules down and think about it. One of these molecules has a boiling point of 5 degrees Celsius, and one of them has a boiling point of 33 degrees Celsius. Which one do you think is which, based on this, what we've learned so far? Think about, well, first, what kind of functional group are we looking at here? Which one has polar bonds? Where are the non-polar bonds? You could label positive and negative partial charges. But what would you predict? Is that the answer you came up with? We can look at the melting point data too, just to confirm what we've already seen. Okay, so in this molecule here, it's an amine. It's a tertiary amine. Remember, the 3 means that the nitrogen is bonded to 1, 2, 3 carbons. And so each of these nitrogen-carbon bonds are polar bonds. And so it's got polar bonds, so that means it's going to have dipole-dipole interactions. And it'll also have dispersion or van der Waals forces. But it's not capable of hydrogen bonding because there's a nitrogen in the structure, but there's no nitrogen-hydrogen bonds. There's carbon-hydrogen bonds, but that's it. We can contrast that with this structure. It has the same exact formula, it's just a little rearrangement of the atoms, and it gives it distinctively different properties. This would be a primary amine. And so in this case, we've got polar bonds here. 2 nitrogen-hydrogen bonds that are polar, and then a nitrogen-carbon bond that's polar. But here, because we have this NH bond, this one has dispersion forces, or van der Waals. It's got dipole-dipole. So the same can be said for both of these, but only this one can hydrogen bond. Just like we saw before, this time with amines, That hydrogen bonding ability makes the boiling point higher. It takes a lot more energy to take this molecule into the gas phase because of that hydrogen bonding ability. Individual molecules like this are stuck together much stronger, being able to hydrogen bond. We see the same thing reflected in the melting points. This is significantly colder of a melting point temperature than this one, so it takes more energy to melt this. It takes more energy to boil this. In terms of water solubility, these turn out to both be water soluble. And so the hydrogen bonding here certainly helps this one dissolve in water, but it's got polar bonds as well. Here, there's enough polar bonds, and the non-polar portions aren't that big, that it's perfectly soluble in water as well. So we'll do more examples in class.